All right, so we are working on EQ number 23 today. You've already done EQs 21 and 22. Hopefully you've gotten some practice in on naming, and you've realized that it's not a joke. Naming can get really hard, but this will actually be just a tiny bit of a break from naming. I just kind of wanted to throw this in there. You'll still have to name, of course, but a lot of Lewis structures. So we talked about Lewis dot diagrams before Christmas break, and now we're just taking single dot diagrams and piecing them together to form full structures. You'll find most dot diagrams, because we are showing sharing of electrons, they're going to be covalent compounds. So naming for dot structures is not going to be that difficult. It's actually drawing them. But I figured we'd go through this first. We'll do a little bit of geometry, not the math kind of geometry, but sort of molecular geometry in the next lecture. But for now, we'll stick to dot structures. Dot structures are essentially like jigsaw puzzles. They're not that difficult once you get the hang of it. So that's what we are going to focus on today. So you've got your EQ. Hopefully you already wrote it down. If you didn't, it's on the wall or it's on Edline. It was on the do now, so you should have written it down then. But it says, what information do Lewis structures provide about a compound? And what are some exceptions to the octet rule? We all know what the octet rule is. We all know that, elements in general want 8 in their outer shell. But we're going to talk about how most of them meet the octet rule, and then how a couple of them break the octet rule. Because as you know, there are exceptions to every single rule in chemistry. So this is going to be a series of steps. So if you guys want to, it's up to you. But if you want to have the sub pause for you to write the steps, and then you can unpause it while I explain, that's completely up to you. But I'll give you a reasonable amount of time to write while I talk. You'll just have to listen and talk, listen and write at the same time. So if you want to pause it now real quick to write down, you're more than welcome to. Okay, so rules for Lewis structures. So we're going to start off with dot diagrams, which you already should know how to draw. So you'll draw the dot diagram for all of the elements involved. That's your very first step. And then just one thing to remember, we remember lone pairs, we leave them alone. Right? Sorry, that looks crooked to me. I don't know if it is, but hopefully I'm not making it more crooked. Maybe I am. I don't know. We'll leave it like that. So remember, lone pairs you leave alone for the most part. As I said, we're going to talk about some exceptions. And then unpaired electrons are the ones that can form bonds. And remember, those are called bonding electrons. And they're called bonding electrons. Crazy to think about, but they're called bonding electrons because they can form bonds. Sorry, I'm just trying to zoom in a little and it didn't work. So, all right, so draw the dot diagram. Remember, leave the lone pairs alone. And remember the number of, or the single electrons, the unpaired electrons, are going to tell us how many bonds each one of those elements can form. All right, so an example, if we're going to work with NH3, we're going to draw the Lewis structure. You can already probably pretty clearly see that these piece together pretty well. But first step is just going to be to draw the Lewis dot diagrams. So we know nitrogen, it's right here, and I can try to draw it a little bit bigger over here. So we've got nitrogen, and it's in group 5, so it's got 5 valence electrons. We've got 3 hydrogen. I'm just going to draw 1 for now, just because obviously they're all going to have the same Lewis structure, or Lewis dot diagram. And then it's in group 1, and it's got 1 valence electron. All right, so next step, and again, pause at any time if you guys are still writing. Next step, see how many of the electrons are unpaired and can form bonds to meet the octet rule. So if we redraw that, we've got nitrogen, right, with its 1, 2, 3, 4, 5 valence electrons. I'll make those a little bit darker. and then you've got 3 hydrogen, all with 1 valence electron. So hopefully you're pointing out or seeing that each hydrogen can form 1 bond, and this 1 nitrogen can form 3 bonds. So notice how well those are going to fit together in a Lewis structure. Right? That's all this step is saying. Figure out how many bonds each one of your elements can form. All right. Next, this is a general rule. Sometimes it gets broken. Most of the time we follow it. It says place the atom that can form the most bonds in the center. So of our 2, hydrogen and nitrogen, which one can form the most bonds? Hopefully you're answering. Of hydrogen and nitrogen, which one forms the most bonds? Hopefully you're all correct and you said nitrogen. We know of our 2, nitrogen can form 3 bonds. Hydrogen can only form 1 bond. So we're going to put nitrogen in the center, and then we're going to build off of nitrogen. All right, so the one that can form the most bonds goes in the center. And again, pause at any time if you need to. Just let the sub know, and he can pause it and then restart it when you guys are ready. Okay, next one. Arrange the remaining atoms around the center atom to satisfy the octet rule. So, already well established, our center is nitrogen, and we've got 3 hydrogens that can all form 1 bond. So hopefully at this point you're like, Ms. Fiera, this is stupid. I already knew how to build this 4 slides ago. That's perfect. That's what I would want you to do. All right, if you place your hydrogens all around, we know nothing's going to bond to the top because there's a lone pair there. We know each hydrogen has 1 electron. So each hydrogen can form 1 bond. Oh, I'm so sorry. I have the top cut off. All right, so we have arranged the remaining atoms around the center atom to satisfy the octet rule for all atoms. And then just as a reminder, remember since hydrogen's in the first group, the first period, period 1, remember it only has room for 2 electrons just like helium. So hydrogen will be completely full and meeting its own octet rule at 2 electrons. All right, so once hydrogen has 2 electrons, once it's sharing its electron and getting another one to share, it would be happy. All right, so we've arranged them. One other hint, this is not always the case, and you'll find that eventually this doesn't work quite as often, but for our purposes right now, it works pretty well. Oh, sorry. I got a text message, but you're more important, so I'm going to put my phone on silent and keep talking. Symmetry is common, so a lot of times what you do to one side, you normally do to the other side. Again, not always true, but usually pretty true. Okay, usually our structures are pretty symmetrical, so if you were to divide them this way or this way, they tend to mirror each other. Okay, in this case, that works pretty well if we divide them, vertically. Right, whatever's happening on this side, the same thing's happening on the other side. Okay, moving on to step number 5. We are going to draw a dash to represent a bond. And then just, it says remember, I know we haven't really talked about it yet, but I don't think it's that much of a stretch for you to have already known this. Remember, a bond represents 2 electrons being shared. 2 electrons. So, again, I'm going to redraw our nitrogen with its 5 valence electrons. I'm going to redraw each one of our hydrogens with their 1 valence electron. I'm going to draw them, on the sides where it would seem like it would make the most sense. And we're going to draw dashes to show that this electron and this electron are going to be shared between this hydrogen and the nitrogen. All right, so instead of dots, draw dashes. Same here. We're going to draw a dash to represent this nitrogen's electron and this hydrogen's electron are going to be shared between the 2 of them. And the same thing on the last side. All right, that is a Lewis structure. So notice you start out with dots, figure out how they're all going to be shared, and then you end up drawing dashes to show the sharing of those electrons. Last step, just check your work, make sure everybody's happy, which we can do. So if you look at each hydrogen, right, so this hydrogen's happy because it's got those 2 electrons, right, the one here that was its own, and then the one here that's being shared. The same with the other 2. Okay, they're all in the same situation. They're all happy because they've got 2 electrons in their outer shell. And then the nitrogen's happy because it's got 8. I know this is going to look a little messy, but the nitrogen's got 8 in its outer shell. It's 2 from its lone pair that we didn't mess with, and then the 3 sets of shared electrons with each one of the hydrogens. All right, so everyone's happy, good, octet rules being met, we're good to go. Okay. A couple of other things. So as it says, remember a bond represents 2 electrons. Well, if you have any experience at all, or if you've even seen other structures drawn, we know that there's not just single bonds that exist. We have single bonds, double bonds, and triple bonds. All right, triple bonds are the most that we'll have. So I actually think you guys should probably pause this for a second to write this information down. And then I'll talk about it a little bit, and then we'll talk about some exceptions, do some examples, and that'll be it. Okay, this is kind of a shorter lecture. So pause it, and then we'll start talking again after you guys are done. Alright, so a double bond. Sorry, like I'm tired or something. By the way, this is the week before Christmas, so you guys are about to take your exams. Not real time, so still no Jameson right now. And I'm actually at home right now instead of in my classroom, so if Naked Face and Garbage Mouth decide to show up, I will be more than happy to share them with you. Alright, but so far they are sleeping somewhere. They are not interested in you, but maybe eventually. Okay, so a double bond is a bond in which 2 pairs of electrons. So think about what 2 pairs means, okay? If you have 2 pairs of something, how many do you have? Let's hope. Everyone got that right and said 4. They are sharing 4 electrons among them, okay, among those 2 elements. It'd be the same with a triple bond, but notice it is 3 pairs being shared, so they would be sharing a total of 6 electrons. All right, and this doesn't happen with all elements. Not all elements can do this, just the ones that are able to form more than one bond. All right, so a double bond is a bond in which 2 pairs of electrons or 4 electrons are shared between 2 atoms. And as it says, this happens when 2 atoms have to share 4 electrons or 2 pairs of electrons in order to meet the octet rule. So oxygen is one of those examples. If you remember correctly, before break we talked about the fact that oxygen is most likely going to exist as O2. It's going to bond with itself if it has nothing else to bond with, because it's generally so reactive that that's what it has to do. It doesn't have a choice but to share with each other, just so that it becomes a little more stable. So if we draw the dot diagram for oxygen, right, so we know we've got 1, 2, 3, 4, 5, 6 valence electrons for oxygen, and there's 2 of them, so we should draw them both. 1, 2, 3, 4, 5, 6. All right, and I'm going to actually, should have already written this down, so I'll zoom in on this a little. Those are such a straight line, I can't even handle it. But, all right, so we've got 2 lone pairs and 2 bonding electrons on each oxygen. So how many bonds can each oxygen form? Hopefully you're saying 2, because each one has 2 bonding electrons. All right, so that's exactly what's going to happen. I'll try to use a different color. These 2 are going to come together and form a bond to be shared. Okay, but notice, is are either one of those oxygens completely happy and stable yet? Well, no, and hopefully that's what you're saying. As long as there are single dots left, not everyone's happy. You cannot have any single dots left over in the end. Everybody has to be paired up for stability. All right, so, sorry. Since the only ones left are this one and this one, those will actually come together and be shared in another bond. All right, so we would draw another bond here and form a double bond. So your overall structure when we're done, draw a little arrow, you would have two oxygens double bonded together. And for now, you do have to draw the lone pairs to show that the octet rule is being met. Okay, so now notice, if we were to look at this oxygen, it's got its 1, 2, 3, 4, 5, 6, 7, 8 being full. And then if you count the shared for this one as well, those are being, that oxygen is also full. All right. Hopefully so far so good. Same idea with a triple bond. So again, you should have already written the words down. I'll zoom out a little bit to talk about them, but you should have this written. If not, it's on Edline. And you can always rewatch the lecture if you need to, or pause it at home. A triple bond is a bond in which 3 pairs or 6 electrons are shared. And again, it's the exact same statement, it's just triple instead of double. So you are given, and now we'll leave it. If you're given C2H2 as an example, so let's go ahead and zoom in on that. C2H2. So let's go through our steps. We need to draw the dot diagrams for each one. So carbon has how many valence electrons? I'll wait for you to answer. Good, it has 4. So 4 single dots, right? And then hydrogen has how many valence electrons? 1. Good. We have 2 of each. We have 2 carbons and 2 hydrogens. So we go back through our steps. We know how many bonds can this carbon form. Hopefully you're saying, well, 4 single electrons means 4 bonds, right? And then how many bonds can each hydrogen form? Good. Each hydrogen can form 1. So which ones are we going to put at the center, the hydrogens or the carbons? Very good. The carbons will go in the center because we know we have to put the one that forms the most bonds in the center. You'll find carbon's always going to be at the center because it can form more bonds than most other elements. Okay, except for some of the exceptions. It forms 4 is pretty much the most we can form on a non-rule breaking basis. So we're going to put both carbons in the center. All right, let's draw our 4 dots around each one. All right, and then we need to figure out what we're going to do with our hydrogens. And remember, we said that symmetrical structures are usually pretty common. So what you do to one, what you do to one side, you tend to do to the other side as well. So hopefully you guys are trying to picture this, that it would make sense to put one hydrogen on one carbon and the other hydrogen on the other carbon. So that's what we're going to do. We'll put one over here and one over here. So now we can probably start drawing some dashes, right, to represent where some bonds are going to form. So the easiest ones to see, obviously, are going to be between the hydrogen and the carbon, this hydrogen and this carbon, and then between the 2 carbons, right? So far that's what we have going on. Now, a note you might want to make, and I'm going to zoom out a little so you can see me write this. Okay, a note you might want to make off to the side somewhere, that's a star, I know I'm really good at drawing them, is no single dots allowed. And then we'll add in the end. Okay, so that's just going to be a reminder to you. You are not allowed to end any Lewis structure with a single dot anywhere. Okay, those are bonding electrons. They must go into bonds. Okay, they have to form bonds. You cannot leave single dots anywhere. Not allowed. Okay, it just won't happen. It's not stable, right? They will all have to pair up at some point and form a bond. All right, so let's zoom back into our example, right, which we have right here. All right, so we're not allowed to have any single dots left over. And right now, each carbon has 2 single dots. Not allowed. Those have to go somewhere. They have to do something. Well, we've already used up all of our atoms, right? 2 carbons, 2 hydrogens. So we can't add anything else to it. Okay, we're not allowed to just add hydrogens wherever we feel like it. We were only allowed to have 2. That's all that's there. So everything's already in the structure. We just got to figure out how to get rid of all those single dots. So the hydrogens are full, right? Remember, hydrogens only need to form 1 bond. So those are both fine. We can't mess with those. So really, it's between these 2 carbons that you have your only option. So what ends up happening is those 2 top electrons are going to come together, and they'll form another bond. So now you've got a double bond. And those 2 bottom electrons will come together, and they will form another bond. So now you've got a triple bond. All right, that's the most that you're allowed to have. You can't form more than a triple bond. All right, so if we're going to redraw this, we've got our carbons in the center with triple bonds between them, and then bonded to each carbon is a hydrogen. Now notice everyone's happy. The hydrogens each have their 2 electrons in their 1 bond, and then each carbon, okay, so if we look at this carbon, it's got 1, 2, 3, 4, 5, 6, 7, 8, so it's happy, and obviously it's a mirror image, so it's going to be the same on this side. Alright, so carbons are happy, hydrogens are happy. Triple bond, they are sharing 6 electrons between them, 3 pairs. Hopefully, so far, so good. This next slide is going to be another one where you should probably pause it and write, and then unpause so that I can talk about it. Let me zoom out a little more. All right. This is the exceptions. Okay, there are 3 exceptions. Well, I guess really 4 if you count hydrogen as being an exception. So I'm gonna leave that up for a few minutes. Well, you guys are gonna pause it. I'm not gonna stop talking, but you guys can pause it, and then I'll talk about each one. Okay. So hydrogen we already know about. It's only surrounded by 2 electrons. 2 makes it happy, right? So that means hydrogen only needs to form 1 bond. Okay, and you can draw that next to it if you want to. Next exception. So if you look at the periodic table, boron's the only element in group 3A that's a nonmetal, right? Aluminum down, aluminum, gallium, germanium. Those are all metals. Boron's the only nonmetal, so it actually has to break the rules as well. So if we draw boron, and I'll do that down here. If it's in group 3A, how many valence electrons does boron have? Good, it's got 3. So how many bonds can boron form? Good, 3. Is boron ever going to be able to meet the octet rule by being able to form 3 bonds, and only 3 bonds? No, right? The most it's ever going to be able to have is 6 electrons, because it doesn't have 4 electrons to share in order to meet the octet rule. So boron's pretty content at 3 bonds, 6 electrons. This is a terrible way to remember it, and it actually makes me sad, even though boron's not a real person. And I talk about them all like they're real people. A way to maybe remember it is that boron's a moron, and he can't get 8 electrons. To me, that's very sad, but they're not real people, so I guess boron doesn't really care what you say about it. But it can only form 3 bonds. It can only have 6 outer shell electrons. It can't have 8. It doesn't have the ability to do so. Okay. The next one is phosphorus, and this is when we start to get a little crazy, but it happens. So phosphorus, we know, we draw its dot diagram, it's got 5 valence electrons. So what it's actually able to do, okay, we already know it can form 3 bonds. And it can do that. Phosphorus is totally fine doing that. Okay, there's plenty of structures where phosphorus only forms 3 bonds and it's happy. There are also other structures where phosphorus is actually able to split apart its lone pair and make them both bonding electrons. So instead of those being, I'm just going to kind of cross them out a little. Instead of those being a lone pair, they will actually spread apart and become bonding electrons. So then phosphorus can form 5 bonds. Okay, and then this is nothing. Okay, those aren't electrons anymore. All right, so you can actually have 5 atoms bonded to phosphorus when it's in the center. Sulfur, you can imagine then, does the same thing. Sulfur's got its 6 valence electrons, right? And normally, in a lot of normal cases, sulfur just forms its 2 bonds and goes on its way. There's plenty of structures where that happens. All right, but there's also some structures where it splits apart its lone pairs and it can form a bond off of each one. So there it actually can form 4 bonds and keep 1 lone pair, or it can separate all of its electrons and form 6 bonds. All right, so to draw that a little more symmetrical, it would look kind of like a sunshine, a sulfur sunshine. All right, so sulfur can also do that, which is what gives sulfur the ability to form sulfur hexafluoride, which is, it has the opposite effect on your voice that helium has. So helium, lighter than air, your voice waves travel faster through it, so it raises your voice. If you were to breathe in sulfur hexafluoride, it's heavier than air. It's about 6 times heavier than air. Helium's about 6 times lighter. So if you breathe in sulfur hexafluoride and then talk, you sound like Darth Vader. And I will actually have to write this into the subplans. I haven't done that yet. But I will have the sub show you the video of Neil Patrick Harris breathing in sulfur hexafluoride on the, I don't know, one of the talk shows. It's very funny. But that's what sulfur can do. This is what phosphorus can do. Boron doesn't meet the octet rule, and then you all know hydrogen can only form 1 bond. Okay, so those are the exceptions. Let's do some examples of each exception. Well, actually, let's do some overall examples. So, first one, I should have brought extra paper. I might end up using the backs of these. Yeah, let's do that. I'll do some on here, and then I'll have to do some on a separate sheet so that I don't run out of space. I'm actually going to take this out from under there because that's for the next one. Okay, so first one, CH3Br. So, in your head or on paper, you can draw out all of the dot diagrams. All right, so we've got, you know what, I might do this up here. So we've got carbon. And how many bonds can carbon form? Or how many dots does carbon have around it, or electrons? Hopefully you're saying it's got 4. Right? And then you've got 3 hydrogens, which can all form 1 bond, right? And then bromine. How many valence electrons does bromine have around it? Hopefully you are looking at the periodic table and you are deciding it has 7. So, how many bonds can each hydrogen form? 1. Good. How many bonds can the carbon form? 4. Great. And how many can the bromine form? 1. If you said 7, your confusion is that you're trying to form a bond from all electrons. Remember, you can't do that with bromine. Bromine's got 7 valence electrons, but notice, lone pair, lone pair, lone pair. You leave lone pairs alone. It only has 1 single electron, so it can only form 1 bond. Okay, so who's going to go in the center? The hydrogen, the carbon, or the bromine? Good, hopefully you said the carbon. So carbon, and notice I drew it in the middle. It's like I'm Harry Potter and I know what's coming next. Carbon's in the center. We've got a hydrogen and a bromine. So we still have to draw our other two hydrogen. Where does it look like we should draw those? Fantastic. Hopefully you're saying one on the top and one on the bottom, right? Next thing you could do or should do is to connect the dots, right? You want to draw dashes where those electrons are going to be shared. So notice carbon can share a bond with that hydrogen, can make a bond with the second hydrogen and the third hydrogen, as well as the bromine. Right, so this is one of those where it's not a symmetrical structure. But same idea. These all can form one. The carbon forms four, so it goes in the center. Hopefully so far so good. Also, hopefully the next one's fairly simple. pH 3. So, phosphorus has how many valence electrons? Hopefully you are all correct when you said 5. And then we've got hydrogen. Hydrogen forms how many, or has how many valence electrons? It's got 1. Again, hopefully you're seeing this pretty quickly now. Who's going to go in the center? The hydrogens or the phosphorus? Good. The phosphorus goes in the center, so that means we draw all the hydrogens around the phosphorus. Each hydrogen has its 1 valence electron. And again, very simple. Connect the dots. Phosphorus is going to bond with each hydrogen. pH 3. Phosphorus is in the center. Each hydrogen is bonded to the phosphorus. You've got 1 lone pair and 3 bonds to the phosphorus. Each hydrogen has 1 bond. Perfect. The next one, Si2Br6. So 2 silicons, 6 bromines. And again, these are like puzzles, so you should almost be able to start picturing them in your head as to how they're going to look. So silicon, how many electrons around it? How many valence electrons? 4. Good. And bromine, we already decided, had 7, right? So 3 lone pairs, 1 bonding electron. So who's going to go in the center? The 6 bromines or the 2 silicons? Great. Hopefully you said the 2 silicons. The silicons can each form 4 bonds. The bromines can only form 1. So we're going to put both silicons in the center, right, with their 4 valence electrons. And if they're both in the center, it should make sense that they're going to have to form at least 1 bond between each other. Now, what does it look like we should do next? We have 6 bromine, right? We already have 1 here. And notice we have 1, 2, 3, 4, 5 more single electrons around our center. So, simple enough. You want to draw bromine on every side of all of your silicons, right? So in the end, you will have 6 bromine all surrounding your 2 silicon in the center. I will tell you, you're going to get so tired of drawing dots. I very strongly suggest you get a marker of some sort, because just, you know what I mean, tapping the paper is much easier than using a pen or a pencil and actually trying to, you know, fill them in like this every time you have to draw a dot. Just get a marker so you can tap them. All right, now everyone's drawn. Start connecting the dots. We have a bond here, 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 and then here, here, and here. Si2Br6, all single bonds. Everybody's happy. Good. Hopefully you're catching on and this is becoming a little bit simpler. We actually might have enough room to do all of these on here. Next one, CO2. 1 carbon, 2 oxygens. Let's draw our carbon with its how many valence electrons? 4. Good. And then oxygens, we have 2 of them. Oxygen has how many valence electrons? 6. Perfect. And we have 2 of them. Who's going to be in the center? The carbon or the oxygens? Good. The carbon has to be in the center, which means we're going to draw our other oxygen on this side. You could draw them on the top and bottom too, but I have more room on the sides, so I'm going to draw them on the sides. Okay, so with the carbon in the center and the oxygens off to the sides, you at least know they're going to have to bond some way, right? So draw the single bonds to connect those electrons. Is everybody happy at this point? Oh, let's hope you're saying no. Okay, notice this oxygen still has a single electron. The carbon still has 2 single electrons, and this oxygen has a single electron. Remember, you cannot leave single electrons in your structure. You have to pair everybody up. Either they're already paired up and you can leave them alone, or you have to figure out a way to pair all of your single electrons up. Hopefully this one's kind of jumping out at you as to what you could do. So what will end up happening is oxygen will bring this electron and carbon will bring this electron to form a double bond. And the same thing on this side. Carbon, which I probably should have drawn that the other way, and oxygen to form another double bond. Right, and that looks a little bit messy, so if we were to redraw it, you guys see that bug? Probably makes me look nuts when I think there's bugs flying around, but there really are. Carbon in the center, double bonds on each side, oxygen, oxygen, and yes, you have to draw the lone pairs in Lewis structures. It's part of the rules. Right, so that's what CO2 would look like. That is not a dot. Okay, 2 lone pairs on each oxygen, and then the 2 bonds between each oxygen and the carbon. Good? Good. Last structure or example is, I think it's the last one, yeah, is N2, nitrogen gas, right? That's what we know we would call it, is nitrogen gas. So it's 2 nitrogens, so let's draw those over here. 1, how many valence electrons for nitrogen? Good, 5. We're going to draw 2 of them, because that's all we have to work with. Obviously designing the center isn't that difficult, it's only 2 nitrogens, so there's not really a center. Quickly, you should see you're going to bond them together once. Again, you cannot leave these single electrons. It's not allowed. They have to do something. So, nitrogen has this fantastic ability. Bring together those 2 electrons to form another bond. And then it'll bring together these other single electrons and form another bond. Alright, so your final Lewis structure for nitrogen is 2 nitrogens triple bonded together, and then to actually draw it the most correct, which I would never, well, we wouldn't take points off for, is you should put the electrons on the sides to show the electrons would spread out as much as they could, but if you put them on top, it's okay. No big deal. Alright, and I'll zoom in on that if you can't see it. Alright, so that's what your final N2 structure would look like. Triple bonds, and then 2, a lone pair on each nitrogen. Perfect. You're good to go. Alright, that's it for Lewis structures. I don't really think there's much else to talk about. You guys have a lot of practice for these. Go ahead and rewatch the lecture if you need to. And as always, Mr. Fear is there to help. Mr. Perkins might be able to help as well. But this was a short lecture, not even 40 minutes, so good for you. You should have some extra time left to chill for a second, okay? Miss you guys, well, I'm actually going to see all of you tomorrow, but in your time, I miss you guys, and I will be back very soon, so hang in there, and I will be back, and we'll finish out the year together, okay? Have a fantastic day.